Welcome to This Explainer. You know, we hear about AI literally every single day, right? It writes essays, it translates languages, it even writes code. From the outside looking in, it feels kind of like pure magic. But I'm here to tell you it's really not. If you strip away all the hype, what you're left with is just incredibly structured, scalable mathematics. So today, we're demystifying AI. We're going to build a mental model together, starting from the absolute simplest mathematical building blocks and logically scaling all the way up to those massive large language models that are completely changing our world. Okay, let's dive into this. How does a neural network actually perform computation? If you boil a computer down to its absolute essence, it's really just doing math. But how do we get from basic arithmetic to a system that can approximate really complex real-world functions? How do we take an input, manipulate it, and get a highly specific, useful output? Well, that is the foundational question we are answering today.
Here's our roadmap for this explainer. First, inside the black box. Second, the power of non-linearity. Third, learning through trial and error. Fourth, scaling up to transformers. And finally, how LLMs generate text. Don't worry, we're starting with the basics and we'll build this up step by step.
Section 1. Inside the black box. The basic math of computation. The absolute core components of all this computation are what we call weights and biases. Think about it this way. Without them, whatever you put in is exactly what you get out. A 3 goes in, a 3 comes out. Pretty useless, right? To change that, we multiply the input by weights. These are just floating point numbers, usually sitting between 0 and 1, that assign mathematical importance to the input. We add those values together, and then we add a bias. The bias just shifts the result to offset any systemic bias. For example, it prevents a scenario where a weight that happens to be a multiple of 2 artificially skews every single subsequent calculation to also be a multiple of 2. So, at this level, we're simply multiplying and adding. We're mathematically pushing our input toward a target output. Section 2. The power of non-linearity. Why simple math isn't enough. Now, if you build a neural network using only linear activation functions, literally just straight lines, adding multiple layers doesn't actually help you at all. Mathematically speaking, a whole sequence of linear transformations just compresses right back down into a single linear transformation. So no matter how many hidden layers you stack in there, a linear network behaves exactly like a simple single layer. It stays completely flat. But think about the real world. The patterns we want to model are incredibly complex. They're messy, they're non-linear. By introducing a nonlinear activation function, our network suddenly gets a superpower. It becomes what's called a universal function approximator. That means it can actually map all those complex, bending boundaries of the real world. And this brilliantly illustrates exactly why the math totally breaks down without that nonlinearity. See, when a network tries to learn, it needs to figure out which specific weights actually caused an error. It does this by calculating derivatives. But the derivative of a linear function, it's just a constant. That means if you use a linear function, your input values have absolutely zero direct effect on how the weights update. Every single weight would update equally, making it literally impossible for the network to actually learn complex patterns from different inputs. Nonlinearity guarantees that different inputs create different, highly specific changes to the weights. It's an absolute game changer. Section 3. Learning through trial and error. How the network improves. All right, here are the 4 basic steps of the learning loop. Step 1, predict. The network makes a guess based on its current weights. Step 2, calculate the error. We use something called a loss function for this. Step 3, send that error backward through the network. This is known as backpropagation. And step 4, adjust the weights using gradient descent. It's just a continuous, rapid-fire loop of calculating mistakes and making tiny, tiny mathematical tweaks. Now, what's really interesting about this is how different loss functions act as a rigorous, unforgiving grader for the network's predictions. The loss function's entire job is to strictly measure how well the algorithm models the dataset. So you have mean squared error, which basically averages the squared differences between the prediction and the real answer. That one's great for predicting continuous numbers, like guessing how expensive rent will be for a specific apartment. But then you have log loss, which is used for categorizing or classification. And log loss has a real kick to it, because mathematically it severely penalizes the network for being very confident but very wrong. So once we have our error, we have to fix it. This is where the amazing partnership between gradient descent and backpropagation comes into play. Think of gradient descent kind of like trying to walk down a mountain while you're completely blindfolded. You have to feel the slope with your feet and take a step in the steepest downward direction you can find. Backpropagation is simply the math, specifically using the chain rule to find derivatives from back to front. It tells the network exactly which way is down, hunting for the absolute lowest possible error. By systematically adjusting those parameters, we essentially slide down the slope to minimize our loss. Section 4. Scaling up to transformers. The architecture behind the magic. Hundreds of billions, sometimes trillions. Up until now, we've just been talking about a few basic weights and biases. But a modern transformer model contains hundreds of billions of these parameters. To put that massive scale into perspective, that is literally more parameters than there are stars in the Milky Way galaxy. It's an almost unfathomable shift in scale. And while normally smaller models are considered more efficient, research has consistently shown that for transformers, just scaling up the sheer number of parameters drastically increases the model's performance. Now, the secret sauce that makes transformers work at this massive scale is called self-attention. To process language, a model absolutely needs context. Self-attention is a mechanism that forces the network to evaluate every single word or token in a sequence and ask itself, how much does every other token in this input affect my interpretation of this specific token? A full transformer model stacks multiple layers and multiple heads of this exact self-attention mechanism. That's how it builds progressively more complex and abstract understandings of syntax, sentiment, and theme. So, the crucial point is how this works in practice. Listen to this sentence. The animal didn't cross the street because it was too tired. As humans, we hear that and we easily know that the pronoun it refers to the animal, but a computer doesn't know what an animal or a street is. However, through the mathematical weights of self-attention, the transformer calculates relevance scores. It mathematically determines that the token animal is far more important to the word it than the token street is, so it assigns it a higher attention weight. Section 5. How LLMs generate text. Predicting the next token. To build an LLM, you need a phenomenal amount of training text, and the method they use is incredibly clever. It's called unsupervised training on mass predictions. It's essentially the world's most massive game of fill-in-the-blank. Engineers hide random tokens, words or parts of words, inside a vast dataset, and the neural network just tries to guess the missing piece. If it guesses wrong, the loss function calculates the error. Backpropagation sends it backward, and gradient descent updates those billions of weights. Through billions of iterations of this exact same mathematical loop, the model actually learns the incredibly complex, higher-order structures of human language. Let's move on and see how this builds into actual text generation. Once it's fully trained, an LLM generates text simply by calculating the probabilities for what comes next. It literally just treats your prompt as the beginning of a sequence with an imaginary mask at the very end. It then mathematically calculates the probabilities for thousands of potential next tokens. So it might calculate a 3.1% probability for one sentence continuation and say a 2.9% probability for another. It then selects the highly probable matches over time, generating the response for you word by word. And that brings us to the real climax of this explainer. Large language models, despite their apparent reasoning capabilities, are fundamentally just massive, incredibly sophisticated autocomplete engines. Everything we perceive as reasoning, creativity, or intelligence in AI is literally just the result of scaling up those basic mathematical operations we started with. It's just multiplying weights, adding biases, applying nonlinear activation functions, and tracking errors through gradient descent, just applied to trillions of parameters. But because it is ultimately just probability and math, the technology has some very real physical and functional limitations. First off, training them requires gathering enormous datasets. They also consume massive computational resources and electricity, often taking months of processing time. Furthermore, because they are essentially just predicting probabilities, they are highly prone to hallucinations, meaning they'll confidently generate statements that are completely factually incorrect. And inevitably, because they learn directly from human data, their mathematical weights will reflect and exhibit the learned biases that are already present in that original text. So we've gone from basic weights and biases all the way up to trillions of parameters generating complex text. And I want to leave you with this thought. If complex text generation, if a machine convincingly replicating human reasoning and language, is ultimately just billions of mathematical predictions, what does that reveal about the underlying mechanics of our own human language? Is our communication also just a highly complex biological prediction engine? Thank you so much for joining me on this explainer, and keep questioning the math behind the magic.